Hello, it's Keith here, and this is lesson 2 of my eZ80 programming tutorials, and we're going to be looking at switching between the classic Z80 16-bit mode and the ADL eZ80 24-bit mode today. And we're going to be looking at executing and jumping between the two, which is quite confusing. We're going to go into in quite a lot of detail. We're going to look at what happens with regards to the two stacks, and it's probably going to get quite confusing, and if it does, I'm going to tell you just don't worry about it too much, because firstly, you're probably going to only need to be in 24-bit mode anyway, and if you do need to switch between the two, to a great extent you can just take it as granted that it works and not worry about what's going on under the hood, so to speak. But for completeness, I need to discuss it and I need to show you how it works. So let's go over to today's source code and let's start taking a look at what we're going to be doing. So this is the lesson 2 source, and we're going to be running it, and we've got a few things. Firstly, we're going to try switching between the two modes and seeing what happens to the stack and seeing how we actually execute classic Z80 mode code from our eZ80 programs and vice versa. And then we're going to go into individual instructions. You see, just because we're in ADL mode, as eZ80 mode, doesn't mean we can't run the odd 16-bit command, and just because we're in 16-bit mode doesn't mean we can't run the odd 24-bit command. So we're going to look at that as well, and we're going to do some very simple tests and see how the commands can be specified and how they actually end up running. So yes, a lot of weird things today, but things that are fundamental to the eZ80, so I needed to cover them. So the first thing we're doing here is we're doing some setup here. Right, well, the first important thing we're doing is we're setting the STMix flag. Now, this tells the processor that we are going to be using a combination of Z80 and eZ80 code. This is important because it alters the way the interrupt handlers work, and it actually also alters the way that items are pushed onto the stack when we call subroutines. And I'm saying that because it confused the bejeepers out of me when I was writing these, because the values being pushed onto the stack I was seeing were 01 and 00, and I was expecting, according to the documentation, 03 and 02. The reason was because I was not setting this STMix flag. Now, if you've got interrupts disabled, it's possibly not going to matter, but if you've got them enabled, you're going to see probably horrendous crashes if you don't set it right. So we're setting it right. The other thing we're doing is we're setting the mbase register, MB. We're setting that to the current area of running memory, and this, if you remember, basically makes up the top 8 bits of our 24-bit addresses when we're in Z80 mode. You can see there's the MB here. So whenever we're doing jumps in the 8-bit mode, that will be the top byte of our addresses. So we need to make sure it's correct. So we're loading that there with the fixed value D1, which is I know where our program is running. Now, just for my development tools, what we're then doing is we're setting IX to a pointer to the start of the current stack area, and IY to the 8-bit stack. And you can see I've got this SIS command here attached to the load and add commands there, and that is effectively setting these as Z80 commands, but classic Z80 commands. And we're going to look at that again later, but I'm doing a one-time Z80 command in my 24-bit eZ80 code here. So that's what we're doing there. We're then adding the base of the memory here, and all of this basically gets the stack for the Z80 mode and stores it in IY. The reason we're having to do that is, if you don't remember, the eZ80 has two stacks. There's the so-called SPS stack pointer for short addressing, that's the Z80 stack, and the SPL stack, that's the eZ80 stack. And when we do a call that bridges over 8-bit Z80 mode and the new eZ80 mode, well, both are used. So we're using IX and IY to point to them so that we can see what's going on. And then I'm dumping a value onto both stacks here. This is a marker to show the start of the stack at the point that this code runs, and then we're showing the stack to the screen. And what we're going to do is we're going to do some tests, and then we're going to see what actually happens as we do branches and what happens to the stack. So the first thing we're doing here is we are doing a jump to long jump test. Now you can see LIL. Now if we specify LIL, this is specifying a long jump. Now if I just go over here, when we specify an extension to our commands like this, we've got LD, and in that case we saw LIL. Now the first L represented the CPU mode, which can be short or long, and the second L represented the parameter length. And this is one of these bits where it gets very complicated, and I would suggest quite simply that you specify all of it every time, and you're probably only going to want SIS mode or LIL mode, but you can omit parts and the processor will fill the blanks in with the current mode. So rather than putting LIL, you could just put .L or .IL and it will fill in the missing part with the current processor state, or you could do IS, and if the processor is currently in eZ80 mode, it would end up as a LIS. But as I say, I'd specify all of it every time just for your own sanity, maybe. I think that's going to work better for you, generally speaking. So anyway, so yes, we can specify an extension to our commands to specify the running mode that those commands should be processed in, and we need to do that to do branches changing the processor mode. So we'll see a few of them here. So for example here, we've got a call command here, and we're calling in long mode to show stack. Now we're actually already in long mode, but this show stack routine is designed to work in either mode, and that means there is a difference to a normal command. Now you'll see at the end of show stack we have a return command, but it's not a normal return command, it's a return.l, return long. If we just put a classic return command, this will crash. The reason it will crash is because there is extra data being pushed onto the stack, which is going to reset the original processor mode. And so we need to make sure we're using the correct return command, so that if our show stack routine is being called specifying a long call, or even if we've got one that specifies a short call, we need to have return.l at the end to tell the processor to take the extra bytes and restore the mode that executed that, so that the processor is back in classic Z80 mode if required, or is in eZ80 mode if that's what's needed. You see here we're calling that routine from classic Z80 mode in ADL equals 0 mode. I'm sure you're probably already confused. It really took a lot of work to get this working, and I don't know an easier way to explain it because it's quite complicated, unfortunately. Okay, so here we're jumping to long code. We've got this long jump test, and then we're just calling our monitor here. So that's going to show the current state of the processor. Now alternatively, we could do a short jump with jump SIS here, and what we've done then is we've specified the label, but we've had to mask out some of the bits so that we've got a 16-bit label here. So short jump test, if we find it, here it is, and this is now going to be in 8-bit mode. Now we need to tell our assembler what kind of code we're actually compiling, because these commands, these ones will be okay, but if we were doing commands that didn't specify the length of the commands and the parameters, the assembler would actually need to compile a different number of bytes. And so we need to tell our assembler what kind of code to compile. This is going to depend on your assembler, but the assembler I'm using, we use the command .assume, and ADL equals 0 for classic Z80 code, and ADL equals 1 for eZ80 commands. So that's how we're telling this assembler what to do. Okay, well, what is our test going to do? Well, our first test is going to call a subroutine. We're going to call a subroutine in short mode, a Z80 routine called Z80 code. And what this Z80 code routine is going to do is it's going to load a long value, specified an override into extended eZ80 mode. We're loading a 24-bit value and we're pushing it to in long mode and in short mode. So we're pushing the same value to both of the stacks, and then we're showing the stack. And we're going to see what effect this has. Okay, well, let's find out what that does. Okay, so here is the stack at the start of our program. We've got that triple F marker and that double F marker on both stacks. The bottom stack is the classic short stack for the Z80 mode, and the top stack with the 3 triple S is the 24-bit eZ80 stack. Okay, so what happens when we call our subroutine with call.is Z80 code? Well, as I say, this routine is pushing this value onto both stacks, but of course the calling of this subroutine will also push some data onto the stack. And because that call occurred before this push, the data pushed onto the stack will be sandwiched between the F's and the E's, and that's why we've pushed those. So let's see what actually happened. Well, here is our 24-bit stack, our eZ80 stack with the triple F there, and then the D1, and then there's an O3. What's the O3 mean? Well, the O3 is to tell the processor that a mode change occurred. Now, O3 means that the processor was in eZ80 mode and it's now switched. So you can see that O3, and the D1 is the top upper byte of the 24-bit program counter. Where have the other 2 bytes gone? Well, they've not got on the long stack, they've gone on the classic short Z80 stack. So you can see the top byte there, D1, then you've got DF and A8, which are the low 2 bytes of the actual address for the return. So to get the return address, we actually need to use both stacks. And that's why we need to return with a retl command. And that return L command will tell the processor to get the 2 bytes from the short stack and the 1 byte from the long stack, and then return the processor mode to whatever it was, and O3 tells it needs to be in long mode. Boy, isn't it confusing? That's what it's unfortunately like. We then popped the E's off the stack here, both of the stacks, and then what we've done is we've called some eZ80 code in long mode. IL is telling it that we're branching out to long mode. And there we've got our assume statement, which is telling the assembler that we're compiling our eZ80 code again. And here's our eZ80 code. We're once again loading all of those E's into the HL and pushing them both onto both stacks. Although you'll notice this time we are just specifying load HL, whereas before we had to specify an override because that was in Z80 mode. We were specifying an override to load in a long value into HL there. So this being in eZ80 code, we don't need to do that. So we've loaded in that value and pushed it onto the stack, and we're calling our show stack again. This time, of course, we're now running from eZ80 mode. So let's see what's happened to our stack. Well, you can see the D1 and the O3 from before, but this time we've pushed another 3 bytes onto the stack. We've got an O2. This is the processor mode, O2 representing short mode because we were in Z80 mode before, and there's another 2 bytes which are the 16-bit program counter address from before the call occurred. Now I think at this stage we're going to be best going over to my documentation here, and we can look at a summary of the mess that is the stack depending on our various callings. So the factors we need to consider are the mode of the CPU before, the mode of the CPU afterwards, and then of course depending on the combinations here, the stack will be affected accordingly. Now if we're in classic Z80 mode, the short stack will take the H and L of the program counter, the return address basically. In long mode, then the long stack will take the low, high and upper bytes of the return address. It's only when we're specifying a suffix things start to get a bit freaky. So if we're in short mode and we call short mode and specify the suffix, then the return address will be put onto the low stack, and an O2 to represent short mode will be put onto the long stack. If we were in long mode and we call short mode, an O3 will be put on the long stack, and the upper byte of the 24-bit address will be put on the long stack, and the return address will be put on the short stack. But if we're calling long mode, then everything will be put onto the long stack. If we were calling from short mode, then an O2 and then the low and high bytes, ignoring the upper byte of the 24-bit return address because it will be the same as the current one. But if we were calling long mode from long mode, specifying the IL extension, then an O3, the low, high and upper bytes will be put onto the stack. Now, of course, these also affect the actual address that is called. If we are calling specifying long mode, then the address will be a 24-bit full address. If we're specifying short mode, however, then the top byte, we can't specify that, which is why I was doing all of these masks here. And this will be taken from mbase, which is the MB register that we were loading in here. As I say, I'm aware this is an absolute nightmare. I apologise. Unfortunately, I think the eZ80 is a fantastic processor when it comes to just using it in 24-bit mode. It's absolutely fantastic, but this switching between modes is extremely complicated. That's not to say that the 65816 isn't any easier, really. It has its own significant problems as well. I can't really say I prefer one over the other. All I can say is that the 68000 didn't have any of these problems, which is unfortunately where maintaining the backward compatibility really makes things quite painful in a lot of ways. So what we're going to look at next is specifying part of all of the extension to commands to specify an override to the current mode. Now, as I say, the commands will be in the format of a letter followed by an I followed by a letter in the complete mode, and as I say, we can omit parts. Basically, the first letter specifies how the CPU will receive the command, so how the CPU will process the data it's given. The I and then the letter afterwards, so the IS or the IL, will specify the kind of parameter that's being passed. So for example, IS will be passing a 16-bit parameter to the processor, so that's a 16-bit parameter, whereas IL will be passing a 24-bit parameter like that. Now, whether the CPU actually takes all of that parameter will depend on the first letter. So for example, in SIL mode, a 24-bit parameter is being passed, but because the processor is in short mode, it's going to ignore the top byte of that. So the A1, A2, A3 that we put in our code will be compiled to the bytes, but the top byte will be lost by the processor, so only A2, A3 will end up in HL. So, as I say, and basically we can override parts of the processor. Generally speaking, I think you'll probably want to use SIS or LIL mode, but the others are available. And you can specify just parts, although again, I wouldn't recommend it. So you can specify just .il, and if the processor is in Z80 mode, it will automatically assume to be SIL, or if it's in eZ80 mode, it will assume to be LIL. So again, that's something you can do, but I would generally avoid it because it might make things even more complicated. Okay, so let's go over to our code and let's try out some of these and see the effects that we have. So we are in eZ80 mode here, and we're going to try out some of these commands. So what have we done here? Well, what we've done here is we've loaded in some test values here. These are just so that we can see a starting position of our processor's registers, and then what we're going to do is we're going to load IX with a pointer to some test data, and you can see the test data just here. That's the test data. And then what we're going to do is we are going to do some tests. So first what we're going to do is jump to test 8-bit full here, which you can see just here, and we are then going to specify the full extension to some commands, and we're going to do each of these loading from IX, specifying the different modes, and we'll see how these registers are actually filled out. Okay, well, let's take a look at what happened. Well, you can see here that these first two values have been loaded in 16 bits, so the top 8 bits have not been filled in, they've been set to 0, whereas the second two have indeed loaded in the full 24 bits. Now, the reason for that is the first two commands were specified that the CPU is working in short mode, whereas the second two were in long mode, and so the processor mode has actually defined the result of these commands. Now, what we've done next is we've loaded all of these registers with new values, and we've attempted to write back. Well, let's see what has happened as a result of that. Well, you can see here that BC has been written back at 16 bits, DE has been written back at 16 bits, HL has been written back at 24 bits, IY has been written back at 24 bits as well. And the reason for that is, well, again, it's the processor mode that has overridden things. And so basically, these are fairly simple in the sense that when the processor mode is set to short, the result is short, and when the processor mode is set to long, the result is long. Now, what we're doing next, though, is we're switching back to eZ80 mode. We're just going to then try those tests once again and see what the result is this time. Well, in this case, the commands all have the same function, and the reason for that is we are actually specifying the entire extension here. So the current processor mode actually makes no difference. What we're going to do this time though is we're going to actually only specify part of the commands, and we'll see what happens now. So this time, rather than specifying SIS and SIL, we're just specifying IS and IL here and here. So this time this will take on the current processor mode. Let's fire this up and let's see what happens now. So once again, we're first doing this in classic Z80 mode. We're specifying the parameter type, but we're not specifying the CPU type here. So here we are. Here we've loaded in our values here. But this time, when we've loaded in, you can see that all of the loaded in values are now 16 bits because the CPU has taken on the Z80 mode of the current running code. And when we've written back to the memory here from the registers, well, you can see here once again only 16 bits has been written back in all cases because the CPU was currently in the 16-bit mode, in the classic Z80 mode. Now, after we've done the Z80 mode, we were running it in eZ80 mode, and we're doing the same tests again here. Well, this time what's happened? Well, this time, because the processor is in eZ80 mode, when we've loaded in the registers, we've loaded them all in 24 bits. The extensions short and long here haven't had an effect on the addressing, so the values have been loaded in full 24 bits. When we've written back, once again, all the values that have been written back are 24 bits. You can see B3, B3, you can see B3, B2, B1, C3, C2, C1, A3, A2, A1, and D3, D2, D1. They've all been written back in 24 bits. So that's specifying IS and IL. The final thing we can do is specify the CPU half of the commands. So this time we're going to specify S and L, and we're going to leave the other half, which is going to be taken by the current running processor state. So if the processor is in short mode, effectively it will automatically append IS, and if we're in long mode it will effectively automatically append IL. Now again, first of all, we're going to run in classic Z80 mode, and we're going to run these commands and we'll see what happens. So we're loading in our values here, and because the CPU is being forced to long mode here when we're loading in HL from IX, it's actually successfully loading in a 24-bit value for HL and IY here. So that's because we are now specifying that the processor is in 24-bit mode. So it's loading in from IX a 24-bit value. And in the same way, when we're attempting to write back, well, B3 and B2 and C3 and C2, those are just 16-bit values, but A3, A2, A1 and D3, D2, D1, those are 16-bit values because, again, when we are specifying the CPU is in long mode, the value that's being written back is 24-bit, but when we're specifying in short mode, the value being written back is 16-bit. So yeah, again, the mode of the processor has made a big difference to the way those commands actually execute. And if you tried with different commands rather than these kinds of load from memory commands, you would potentially get different results. As I say, if you were loading things like immediates, you would get a different result, and you might get different results as well depending on your MBase. If you were running from eZ80 code, it is very complicated, unfortunately. So that was the classic Z80 mode. Now we're going to try the same commands in eZ80 mode, again specifying short and long processor mode, and let's see what happened this time. Well, when the processor was forced to short mode, we've only loaded in 16-bit values there. BC is just 2211 and D is 2211, but HL and IY of course have loaded in full long 24-bit values there. When we write back, once again, because the processor is being effectively forced to short or long mode, well, when it's forced to short mode, of course, it's only writing back 16 bits. So you can see B3, B2, C3, C2, but when it's in long mode, it is able to write A3, A2, A1, and D3, D2, D1 there. So again, the processor mode has affected the way the values are written back. Now, as I say, generally speaking, I'd suggest you try and just stick in 24-bit mode. Now, the only system I've come across that actually supports the eZ80 is the TI-83. I guess if you're doing some kind of hardware project where you're using it as a slot in for a classic Z80, maybe you would just be running it in classic Z80 code. But for the TI-83, I don't think you probably want to switch to Z80 mode at all if you can avoid it. Anyway, that's all we're going to be covering today. There is going to be one last lesson in this series covering outs and ins. We're going to be looking at the in and out commands, and the eZ80 has a lot of new weird commands which we're going to be trying out. And it's actually quite tricky to get outs and ins to work on the TI-83 because it tries to stop you, but it doesn't stop you well enough to get around me messing it up. So we'll be having a look at that next time. As I've said before, if you're interested, I do have a book on classic Z80, which is a lot easier than the confusing stuff we looked at today. It's available on Amazon now. It's called Learn Multi-Platform Assembly with Chibi Akimas. Please check it out if you want to support this channel. I hope you've enjoyed this. I hope some of it made sense. Thanks for watching today, and as of course, always get the source code from the website and try it out yourself. Thanks for watching, and goodbye.